Hey guys, welcome back. I am, as usual, Chili, and this is lesson 12 of the Advanced series. Today we're going to be talking about a topic near and dear to my heart, sexturing. Not texturing, but sexturing. Why? Because I gotta. No, because I'm not wearing a shirt today, so that's the sexy part. Okay, enough of that. So, last lesson I set things up and I talked about lerping, or linear interpolation, which is, again, not to be confused with LARPing. Just want to make that clear. And now we're going to figure out exactly how we lerp or linearly interpolate our texture coordinates in order to figure out which texture pixels to use to fill the pixels on the screen. Okay. So the first thing that I want you guys to know about linear interpolation is that you've already done it. You've already seen this, so it's nothing new. Alpha blending is just linearly interpolating between two different color values in 3 color channels. So for example, you have your source pixel, you have your destination pixel, and what you're doing here is you multiply, I think C is the source pixel, right? So you multiply your source pixel by some value, and then you multiply the destination pixel by basically the complement of that value, and then you add them together. So the basic formula here, again, and I've explained this I think in the beginner tutorial series, but never hurts to do a little review. You've got 2 values, a and, no, we're not going to say a and b, you say x and y, and you want to interpolate between them. What you do is you go x times alpha plus 1 minus alpha times y. And that will interpolate between x and y, where alpha has to be, alpha is a value between 0 and 1. Alright? So obviously a value of 0 in alpha, 0 times x is going to be no x, and 1 minus 0 is just 1. So when alpha is 0, you just get y. When alpha is 1, you just get x. And when alpha is between 0 and 1, you get some combination of x and y. That, my friends, is linear interpolation. The problem is, of course, I didn't explain this diagram yet. I guess I should do that. Although I hope it's fairly self-explanatory. Okay, so what you got here is you've got your texture. Then you've got a triangle in model space. And the vertices of this triangle are mapped to coordinates on the texture. That's your UV mapping. UV mapping. Wow. So these colors indicate the mapping here. And this is the actual texture after, or not the texture, the triangle after it's been transformed from model space into screen space. And these are the corresponding vertices in screen space. And of course, as you guys know, when you draw a triangle, you split it up into a flat top and flat bottom. So we've done that here in the screen space. And then we find the new vertex that's added to create the 2 triangles. And we also, because every vertice or vertex has to be associated with a coordinate in texture space, we also calculate the texture coordinate, the UV coordinate in the texture for the new vertex here. So that's what this diagram is showing. Now, like I said, we know how to interpolate between 2 values, but how do we interpolate between 3 values? That's another story. And it's a story that I would like to tell. Alright, so here's the idea. Now we know that as we travel inside this region here, the corresponding texture coordinate is going to be some combination of the red, the green, and the aqua here. I don't know what this color is. I'm going to call it aqua. So for example, if we're here, we would expect our texture coordinate to be somewhere around here. If we're in the smack dab in the middle here, we would expect to be here. If we're closer to the teal, we would expect it here. If we're right on this texture coordinate, then we know we're going to be here. We know that for sure. We know that if we're here, we're going to be here. If we're here, we're going to be here. If we're here, we're going to be here. So as we move from this edge to over here, we're going to be getting less and less of the teal and more of the green and the red. And when we move on this line here is going to be somewhere between the green and the red, meaning the teal is not going to count as at all. So as you move from this side to this side to here, in this direction here, you're going to get less and less teal until you're just all some combination of green and red. So what this means is that along this line, you're doing a straight linear interpolation between only red and green, which means we can use that formula that I talked about before, the alpha formula, right? So along this line, all we're looking at is alpha red plus 1 minus alpha green. Okay. So what is our alpha? Well, our alpha is going to be our y coordinate in screen space here. Think about it. If you go halfway down the triangle here, then you're going to be halfway between here and here. So we use this, the relative motion in the y along this triangle as our linear interpolation parameter. So what you do is you take, let me think here. You would take y minus, let me think here. We want to subtract, so you take y minus y red, right, divided by y green, maybe. So if y is equal to y green, y green minus y red? Yes, I think that's what it is. And then in this case, if y is equal to y green, this would be equal to 1. And if y is equal to y red, this would be equal to 0. So now we get a value from 0 to 1. And what we do then is we take this, we say that this is equal to alpha, and then we go alpha times our green value plus 1 minus alpha times our red value. And that, my friends, will give you your interpolation between these two. Now there's one more thing. We could use this formula and calculate the texture coordinate for every point along this line, but what we're going to do is something a little different. We're going to take the texture coordinate here, and then we're going to calculate the change in texture coordinate, the change in UV, every step along the y-axis here. So for every step, how much of a change in UV do we get? So going from red to green, it's going to be this way, right? And so how far down here do we go for every step in the y? And that's what we're going to calculate. We're going to call that delta T for delta texture. And then every step, because eventually what we're going to want to do is draw this triangle scan line by scan line, you know, marching down in the y direction. And for every time we march down to a new scan line, we're just going to take this value or our previous value here, previous starting value, and we're going to take t and we're going to add dt to it to give us, you know, our new t, which would be, I don't know, t primed or whatever you want to call it. So yeah, instead of calculating it from scratch every time, we're going to find the delta, and we're going to add the delta to our previous value. So this, you would add delta to this one to get this one, then you would add delta to this one to get this one. And that would move you down like this in texture space until you get here, and you would end up here. So how do we calculate our delta? I'm just going to clean up my space here. Let me think here. Our delta will be calculated by taking the difference between green and red. So we go green. Now green and red are actually vectors, right? Because they're UV. They're two-dimensional vectors. So we do green minus red, and that will give us this vector here. And then we divide by this total distance here, the total number of steps you take from this start point to this end point in the y direction. So that would be green, red minus, if this is vertex 0 and this is vertex 1, then we would go v1y minus v0y. And this will give us, is equal to dt, delta texture, which is also a vector. Yes. Okay. So we're making some headway. We can calculate our texture coordinates along this line here. But obviously we want to fill in more pixels than just the pixels along the line of the triangle. We want to fill the ones inside. But what we're going to do is we're going to calculate these texture coordinates, and we're going to do the same thing along this line here and calculate these texture coordinates. And then what we're going to do, so we start a scan line, we calculate the start, the end, by, you know, interpolation, and then we do the same thing in this direction to calculate interpolation between this start texture coordinate and this end texture coordinate on the scan line, and then we march along the scan line in the x direction, linear interpolate to find our texture coordinates, and then fill them in with those texture coordinate values. So as we move, you know, in this direction along the triangle in screen space, we're going to be moving, let me think here. We're going to be moving in this direction in the texture, in texture space, in UV space, whatever you want to call it. And that's basically how you do it. You interpolate between your vertex UV coordinates to get your start and your end lines, and then you interpolate between the start and the ends to get your points in the triangle. It's that simple. You just break it down into two separated linear interpolations and you're all good to go. And that's what we're going to be doing. Now there's a couple of caveats. I had a lot of trouble in the beginning getting this to work. What I initially went to do is I just tried to modify the triangle drawing code we already had for texture mapping, and what I got was this bullshit. If you look at this, you can see that this is fucked up. There's an error in the triangle texturing here, and when you split a single triangle up into two flat triangles, if one of them is really skinny, the error is really prominent. If they're split up pretty evenly, if the triangles have fairly good height, you can't really tell the error that much. But as soon as you split the triangles up into one of them getting really skinny, then you see the error. And I tried a bunch of shit. I couldn't fix it. I had a bunch of stuff, you know, just life stuff dragging me away from the tutorials, and I just really didn't want to get down into it. Eventually, I just decided to start from scratch. And one of the things that I had a candidate for what my problem might be was, okay, let me just show you something here. This is a nice resource on the internet, all about texture mapping. It's a very detailed tutorial series on texture mapping. And we're going to be referring to it a little bit here. I'll link it in the description if you guys want to take a look at it. Talks about a bunch of bullshit. But one of the things that I thought my problem might be was I thought my fill convention might be fucked up. Because originally what I had been doing is sort of just winging it and saying, okay, well, I guess if I add 0.5 and, you know, convert to int, then it'll round to the nearest integer value and it'll be okay, maybe, I guess. And it's actually not that bad, but it's, I don't know, it's not the best. And I figured maybe my problem was in there. So I read up on fill conventions here and I tried to implement that. And it turns out that that wasn't the problem, but we're going to be using this fill convention anyways. What we use is we use the ceiling function and the floor function, I believe. Or maybe just the ceiling function, I can't remember. I don't want to actually, you know, go over all this, but you can read it if you like. It's a section starting with conventional wisdom. And, you know, and then in this find your texture here. Let me just take a look at this here. Yeah, okay. So, yeah, this is one thing that's, you know, something you have to take a look at. Fill conventions. And the other thing, and the thing that actually ended up causing the problem, was pre-stepping. Pre-stepping your texture coordinates. And that is a big thing. Now, the idea is, first of all, your pixels, they're centered at their coordinates. So a pixel of, let's say pixel 0, 0, has its center at 0, 0, and it extends from negative 0.5, negative 0.5, to positive 0.5, positive 0.5. And what we're going to be doing is we're going to, when we're drawing sampling textures for our pixels, we want to make sure that we sample from the center of the pixel in the screen space and use that to calculate the texture coordinate. Now the problem is that the line of our triangle is a floating point number. It's not going to line up perfectly with any textures or any pixel centers. It's going to be off center. So you have to start your loop to, you know, look up your texture values and fill in your screen. You have to start that loop away from the actual edge of the triangle. So you're not going to be starting at the edge of the triangle in screen space. You're going to be starting some ways away from the edge. So that displacement, that difference from the real triangle start and your screen space start, has to be reflected also in the texture. So if you step a ways into the space in screen space, you also have to step into the space in texture space. Otherwise, you get dumb bullshit. And that's called pre-stepping. So let me see if I can draw out a quick example here. So let's say we're going to make really low resolution here. Here are pixel centers. 3. Yeah, they're not the best, but they'll do. All right, so all these pixels are inside the triangle. This one's right on the edge of the triangle, but since we're at top left fill convention, this pixel will be lit up. Alright, so what do we got here? So first off, we're not going to start scanning our scan line here. We're going to start our scan line here. So there's going to be a step into here. So we need to immediately pre-step a little bit in this direction here. Well, actually, a pre-step is going to be like this. I don't know, man. We're pre-stepping in this direction here. So we're going to get a little bit of pre-steppage here. I'm going to start here. And then, you know, move along in this way. And, well, we'll figure it out as we code it up. I don't want to, you know, explain it in too much detail here. The idea is that you're not starting right on the real edges of your triangle. So you're not going to be starting on the actual edges of your texture either. You're going to be stepping into the texture. And that will fix most of the problems that we have. So now comes the fun part. We gotta code this motherfucker up. And like I said, we're not going to be... Oh, that's the wrong one. We're not going to be... where is it? Where am I? We're not going to reuse, or we're not going to modify this draw triangle code and stuff like that. Instead, we're going to start from scratch, although it's going to resemble draw triangle in many ways. It will not be exactly the same. But first, we have to create a new kind of data, right? Because in our model space here, our texture, our triangles will have 3 vertex coordinates in model space, but they'll also have texture coordinates, UV, that map to space, or coordinates on the texture that you'll be using to render the triangle. So we want to take the triangle coordinates, the vertex coordinates, and the texture coordinates and bind them together in a single data type. So let's do that. We'll go here. We'll add project, add new item, header file, and we'll call this one vertex.h. We'll add that. Then Chili is gonna do something over. I wish I had another monitor. Let me switch my branches here. And we'll go to rote scale. And where did I put my vertex information? Probably in graphics.h. Which is where? D3D graphics.h. There we go. All right. Where is my stuff? There it is, vertex. So, we're gonna make this. I'm just gonna copy this. We're gonna put this here. I'm gonna go # pragma once, # include. No, we want include vec2. And here we want to go vec2 and vec2. Okay, why don't you like that? Oh, wait. Probably because it should be called vec2.h. All right, and then we just define a couple of simple utilitarian functions here. An assignment operator, so we can, assign one vertex to another. And a swap function to allow us to swap the contents of, 2 different vertices. So you guys can, type this out. It's not much, but it will come in handy. Now we're going to go, let me think here. So we're going to have 3 functions. Let's go to d3dgraphics.h. So what are our functions? Well, Where's draw triangle? Here it is. Draw triangle. We don't, okay, transblit can go eat a bag of dicks. We don't need that anymore. What we want is void draw triangle text. In D3D graphics, we want to include vertex.h. And there we go. Now, draw triangle text is going to be vector v0, vector v1, and vector v2. Why did I say vector when I meant vertex? Mysteries of the universe. Here we go. That's all good. So we got our 3 vertices. We'll also add a rect eye for clipping and surface for texturing. We'll make that constant. This rect eye will be constant, I guess. I don't think we need to change it. And there we will have our draw triangle text. Now, as a the draw flat triangle, I want to make this private, to be honest with you. Just because it's not really the function you want the user to be exposed to. We're going to cut this out. Go private. Draw flat triangle. Now what we want to do is copy draw triangle text. And we want to draw flat top triangle text and draw flat bottom triangle text. And they're going to all take the same parameters. So that is simple. Now that we have that all set up, let's switch over to our CPP file. Let's kill transblit because we don't need this. This was just some bullshit to show you why the naive solution will not cut the mustard. And now we got to get into making our functions. So we'll start at the top level function, which is just the draw triangle text. I'm going to toggle again. I'm going to copy this signature. Toggle. Paste. Then we got D3D graphics. That was dumb. There. All right, what's your problem? Okay, good. No problem. Now, what to do? Well, first thing is simple. We still need to sort our dumb stuff. Only now we can't really compare our vertices because you don't have a comparison operator. So what we need to do is we need to compare their components. What I'm going to do is I'm going to go to definition of vertex. I'm going to make sure. So I named it P and Q for the vertex components. I'm going to change, I'm going to change P to V. I'm going to change Q to T. Just because I think that might be a little more intuitive, maybe? I don't know. So we're going to go V1 dot V We're just going to keep doing this all over here. So we're comparing the screen space coordinates here. And then if the comparison is less than, not the order that we want, we swap the vertices. We don't swap the components. We swap the whole vertex, texture, and screen space. All right, so first part is done. We got our triangle vertices all ordered up. Now the next thing is we want to check to see whether or not we have just a simple flat top or a simple flat bottom triangle. So, because that simple case would, make our life easier. So again, nope, that's the wrong thing. I'm gonna copy this. I'll put this here, put that there. This swap wheel is another thing that we're going to want to look at. That's to make sure that V1 and V2 are in the correct order in X space. So this is going to be the case of a flat top triangle, right? Draw. Okay. All right. Now, if you remember from, whenever I did the tutorial on drawing the motherfucking triangle, what we ended up doing was when we split a triangle like this, we ended up calculating the slope from here to here and using that same slope and intercept for this segment and this segment for the two different triangles. And that was to make sure that when you had different triangles, that were bordering each other, you wouldn't get gaps in between. And with my new method of rendering, we don't actually need to pre-calculate the slope and the intercept. It works mostly, I'd say like 99.9% of the time. There's no gaps in between, which is good enough for me. And it does that without calculating the slopes. So we're not going to use slopes in our new system, which you could have already guessed taking a look at draw flat top and flat bottom triangle text. We just pass in 3 vertices. We don't pass in, intercepts and slopes. So that makes things a little easier. So once we get here, we do flat, draw, flat, top triangle text, and we just do V0, V1, V2, and clip, not chip, but clip, text. And that should be all she wrote. And again, the same story here. We check to see if we got a natural flat bottom triangle. And if we do, we reorder the vertices on the bottom to make sure that, V1 is to the left of V2. And then we just draw our flat bottom triangle. So far, so good. Now here comes the slightly more interesting part. And by slightly more interesting, I mean more pain in the assy. Where we gotta toggle this mother. So what have I got here? Alright, so what I need to do next is I need to calculate the intermediate vertex point and calculate the UV coordinates for that point. Which means what I'm trying to say is I need to calculate this teal point here where we split the triangle, and I also need to calculate its corresponding point in texture coordinates. So how we do that is we use these beautiful, beautiful formulae. which I will explain after I copy and paste them. I don't want to type them out because if I might fuck it up, and that would be bad. I will, however, fix them so that they work with our framework. I'm going to change vec2d to just vec2. Now it says v3.p. It should be through v3.v, v, 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 v. That game has a pretty good soundtrack, if you ask me. Oh yeah, and this is v2 or v3. Oh, okay, that's fine. v3 has to be v2. v1 has to be v0. v2 is v1. v1 is v0. v1 is v0. v2 is v1. All right, that fixes that up. All right, so what is this calculation? Oh, wait. So I'm going to call this one vec2v. So this is calculating the point in screen space for the splitting vertex of the triangle. I don't know why I'm talking like this, but so writing this in just plain mathematic languages would be, what is this? This is the difference. All right. I want to look at this, but I also want to look at this at the same time. My setup is just not ready for that kind of technology. No. Wait, what if I go in this direction? Oh, yes. Now we're cooking with gasoline. Wait, don't cook with gasoline. That's a bad idea. From a flavor standpoint and just from an anything standpoint. What we want to do... Alright, so we got V... This is V0. This is V1. This is V2. So what we're doing is we're doing V2x minus V0x. So we're finding this distance divided by V2y minus V0y. So what we're doing is we're getting this slope. But it's not the rise over run slope, it's the run over rise slope. So it's the inverse slope. So it's saying how far do we go in the x direction for every one step in the y direction. And then we're multiplying that by our change in the y direction between V0 and V1. So we're saying when we move only this much from here to here, in the y direction, we move only this far in the y direction, how far do we go in the x direction to get to this point here? So we're only moving this much. How far do we go? We go this far. And that gets us this distance here. And then we add this to the x of V0. So we take this one, we add this distance to get this x. This is our x coordinate for the splitting point right here. And then the y coordinate is just this thing here. And that's just because we already know where we want to split. We want to split on the y coordinate of V1. So that's just this. So we get our x for splitting, we get our y for splitting. And there we go. We've got our point here. Capiche? Now this next one is calculating the corresponding point in... you know what? I better undo all this because it's going to fuck up my diagram. Worse than it's already fucked up, which is pretty bad. Alright, so the next thing here is calculating texture coordinate points. T. And again, we gotta subtract 1 from each one of these subscripts. V0, V2, V0. All right. P. What is P? P is nothing. It's all about the T's. So we got T, T, T. P, 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 P. No. V, 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 and V. There we go. Down here is going to be V and T. Okay, so what are we doing here? Calculating the UV coordinates. Well, let's see if I can scroll along here. So V0 dot T is going to be right here. So we're starting here and we're adding something to that. And we're doing vector math here, so we're adding a vector to this vector. And the vector is going to be V2 minus V1. So that's the vector between V2 and V0. So that's this one. This vector times Vy minus V. What does this mean? So this is the difference in, this is screen space, right? Because it's V's, not T's. So this is the difference between the split point Y and V0. So that's this distance here, not a vector quantity, just a normal scalar, divided by this distance. So this is basically the ratio of how far down the split point is along the triangle. So if it was halfway down, then this would evaluate to 1/2, for example, right? The whole length divided by however far we're going down to get to our split point in the y direction. So we're taking that ratio, how far we're going down the triangle, and we're multiplying it by this vector to go from V0 to V2. So if we're going all or halfway down the triangle, then we want to multiply that to get half of this vector here. Because then yeah, that makes sense. That makes sense. Because if we're going to go halfway down the triangle, halfway from blue to green, wait a minute. Okay, I'm dumb. It should be this one here, right? Because when originally this was V0, this was V1, this is V2, right? However, we reorder the vertices so that they go in order of Y. So it would be 0, 1, 2. So this would also be 0, 1, 2. So 0 to 2 would give us this vector here. And then if we want to go down, let's say this is 1/3. We have to go 1/3 down the triangle to get to this splitting point. We also want the texture coordinate that corresponds to this point to be 1/3 down here. Well, it's less than a third, but you get the idea. And that's how we calculate the texture coordinate for the new split point, the splitting vertex. And then we just we compose the vertex by saying, this constant vertex Vi is equal to the vector for screen space and the vector for the UV coordinate. And there you go. That's how we calculate our new splitting vertex. All right, we're just motoring along here, not really, but we are almost done. So now we just have to determine what case of triangle we have. major right or major left, which, if you will remember, yeah, that's about right, I guess. Okay. If you will remember, major right means that the splitting, the edge that has to be split is on the right hand side, whereas major left, it means that the edge that has to be split is on the left hand side. So we determine that by determining is the new vertex to the left or to the right of V1. If it's to the right, it's major right. If it's to the left, it's major left. So I'm just going to copy this from the old, not the old project, but from my test project. And I'm going to paste it in here. So if major right, so we go V, which means, yeah, it's major right if our new vertex, wait a minute, I don't buy this. Well, it works, V. Yeah, I guess we could compare this V instead of using VI. It doesn't matter which one we use. I want to use VI though. It seems like the right thing to do. So there we go. VI, vertex in screen space, compare its X to V1. That could have caused problems. V1, which is this vertex here. And if it's a major right triangle, then we want to draw text and clip. Like this. This has to be 0 and 1 again. This one has to be 1 and 2. Why is text bad? Why don't you like text? And clip text. Okay, it's a thing, but you don't want to do it. Draw. Why? No suitable from constant surface to constant. Oh, I got them backwards. Okay, whatever. Clip text. Get rid of that. Clip text. Right. Yeah, because if it's major right, you want V0, V1, and VI for your flat bottom triangle. Right? V0, V1, and VI. Whereas if it was the other way around, you would want V0, VI, V1. Yeah. So do that same bullshit down here. Like so and like so. V0, VI, V1, VI, V1, V2. And I believe that that is all she wrote for the top level function. But we still have our good old friends, the draw flat bottom and flat top functions, which are where all the fun happens. So let's get right down to that. Whew. All right. But we're doing it. And it's going smoothly, mostly because I'm copy and pasting a lot of stuff and then explaining on the way, which cuts down on my horrible typing. Let's toggle header and code file. We're going to copy draw flat top triangle. We're going to toggle. Paste that in there. D3D graphics. And away we go. All right, so what do we want to calculate first. Draw flat top triangle. First, we're going to calculate the slopes in screen space for traveling along this edge and traveling along this edge. So I'm just going to copy this. Now the slope, again, remember. One thing remember. Kalakasia. If you know what that's from, then I applaud you. Here we go. Now these slopes, again, are the run over the rise. So they're how far you move in the x for every one move in the y direction. So we need to 2, 2, 0, 1, 2, 2, 0, 1, and we're going to change all these to V's. Stop it. Yeah. I'm starting to get hungry. This is not boding well. Okay. So this is our how far we change in x for every one step in y. Fairly simple. Let's move on. Now we want to calculate the integer start and end scan lines. Right, they have to be integers because, you know, screen actual pixels, you can't have a pixel at, you know, 0.5 x, 1.2 y. That's not how it works. You need them to be integral values. And this is where our fill rules are going to start to come in. Stop opening up shit that you're not supposed to open. I want you. So what does this bullshit all mean? Anyways, why is... Okay, good. Int ceiling. So wait. First of all, v0, v2, and we want v, and we want b. That should fix... Oh wait, now clip rect isn't a thing. Right. So what we're doing is we're taking the ceiling of v0 y. So v0 y is right here. Wait. No, it's not. This is a flat top triangle. Therefore v0 y is right here. Now the ceiling y would be here. The ceiling function basically says for example, if the input is 1, output is 1. If the input is 1.1, the output is 2. If the input is 1.9, the output is 2. If it's 2, the output is 2. So it bumps it up to the next closest integral value. That's all that ceiling does, which is what we want to do. Right? If our line here, if our y value is right on a pixel, right on an integral value, we want to keep it there. But if it's a little bit below, we want to bump it up to the next one here, because this one isn't actually included in the triangle then. So we want to bump that shit up. But if it's right on the line, then we want to keep it there. Now the maximum here is basically saying that if y start is, you know, like a negative, for example, if it's a negative value, right, it's off the screen, off the top of the screen, then we want to take the top value of the clipping rectangle. So we don't want to start above our clipping rectangle because we don't want to draw outside of the clipping rectangle, because that would defeat the purpose of having a clipping rectangle. So we're only going to do scan lines that are within the top and bottom of the clipping rectangle. Now at the bottom, again, we do the same thing. We take the ceiling, but we subtract 1. And what that is saying is, where's my thing? That's saying, for example, we have a triangle like this, and it's right on one of the pixels, because we have a top left filling convention, the bottom, even if we're right on, we don't fill that one. Because that's going to be filled by, you know, say this triangle here is going to fill this one. So we're going to start here. So we take the ceiling, we bump up to the next one, and then we subtract 1 from that. And that gives us our bottom. And again, we use minimum this time to affect the clipping rectangle at the bottom. So far, so good. Now we have to do the thing that I was explaining before. We have to calculate the steps along the edge of in UV coordinates for every step in Y step in the scan line. So we move one scan line down. How does that affect our UV coordinates at the two edges of our triangles? So we take this. Bam. And we got vec2, vec2, Q edge step. I'm going to change Q to T for texture. Edge step, and V2 is going to be, or V3 is going to be V2. So it's going to be V2. It's going to be 0, 1, 2, 2, 0, 0. Q is going to be T. I don't know why I picked Q for the vector coordinate, or for the UV coordinates, texture coordinates. Seemed like a good idea at the time. Okay. And I've already explained this, but basically it's taking the, where? It's taking the difference between, well, it depends on, you know, where you are, but for example, if you're on the left edge here, it's going to be taking the difference, wait, this is flat top, right? Yeah. So it's going to be taking the difference between the red and the green here, and then multiplying it by how, wait a minute, by just the distance between here and here. So the height of the triangle in screen space. So for every one step in screen space in the Y direction, how far do we move along the texture in texture space? Yeah, because V2, V0 is just the whole Y length of the triangle in screen space. And we're dividing the whole change between two vertices in texture space. All right. Next thing to do here. Now we calculate the pre-step. So this is how far do we step in how far do we step along our lines, our triangle edges? We want T edge step, T edge step. We want this one to be T, this one to be T. Y start, Y end, this is a V, this is a V, right? So again, we're drawing this triangle here. Now the actual pixels are like this. So our start scan line, we're going to be starting here. Wait. Our Y is going to be starting here. Whereas our actual Y in our triangle is here. So we have a little bit of a differential between our actual start Y and our actual Y of a triangle. And that means we have to step in a little bit along this direction here. Just a teensy weensy bit. Which means we have to pre-step into our texture just a little bit in this direction. And that's what we're calculating. We're calculating the pre-step here and the pre-step here along these edges. The edge pre-step. And to figure that out, we just do the amount that we move, or first we take the starting texture coordinates, for these vertices, and we add to that the amount of step times the amount of Y movement for the pre-stepping in the screen space. The difference between the actual top of the triangle and the actual, or in the scan line in screen space. There we go. There's our pre-step. And now we start our loops. So where's my stuff here? Right, so we're going to start looping when Y is going to start at Y start, and it's going to go until Y end, inclusive. We're going to include that final Y end. And for every iteration of the loop, we want to obviously add 1 to Y to keep marching down the scan lines. And also we want to add our edge step. Oh wait, I want to rename this to T edge. T edge. T edge. Texture edge right. So we, for every 1 step in Y, we want to add our UV steps to our left and right edge starting things. So every time we move down 1 scan line, we want to add our delta values for these right and left edges to get these texture coordinates here, which correspond to, you know, these ones here and here in the texture. Next. All right, we're getting there. Now we calculate the start and end points in the x direction. So we the start and x coordinates. And again, this is, let me think here. This is a little bit tricky. Right. Okay. So our slope is basically how much we move in the x for every motion in the y. And this here is saying how far, this is our current y for the current scan line, and this is the y for basically just the top of the triangle. So V1, V2, their y's are actually the same. There's no real reason to use different ones for a flat top triangle. But anyways, so we're taking the distance we move. Where's my pictures? We're taking the distance that we move from the start to our current scan line and multiplying that by the slope to get the distance that we moved in the x for that much. And we add that to our start x, which is right here, and that will give us our starting x position along the side of the triangle in screen space. A real start. So let's copy that. Thrust. I sure hope this stuff is sort of making sense. I'm losing my confidence that this explanation is going to be coherent. And now I'm in Japanese typing mode for some reason. Don't do that anymore. Yeah, there we go. Okay. PX1, PX2. M1, M2. Okay, well, I could have made that M0, M1, but whatever. Fuck it. I ain't changing it now. Or am I? Maybe I am. M0, M1, PX0, PX1, M0, M1. I just made more things to change for myself. Wow. Ain't I just the smartest? Now we calculate the start and end pixels much in the same way that we did for the start and end scan lines. We use our fill rules and we use ceiling and ceiling -1. This is the same thing we did as for here, for the scan lines, but it's in the x direction, or the x coordinates now. So I'm not going to give another semi-detailed, semi-incoherent explanation thereof. You can refer to the explanation for the other bullshit. And we don't have clip rect, we just have clip and x0, x1. All right. Oh, now we're making speed. We're making headway now. Now we calculate the UV step along the scan line going right. So this is, let me just reformat all the bullshit. T scan step is equal to T edge R T n px1 minus px0. So what px1 minus px0 is the distance from the start to the end of the scan line in the x direction, the x distance. And we're saying how, so for 1 unit change in the x direction, for every 1 step in this direction, how much do we change in our texture space? How far do we go? So we take the whole change in the texture space, which is the difference between this texture coordinate and this texture coordinate, that's the whole change, and we divide it by 1 step along here. We divide it by the whole change along here. We divide this vector by this distance, and that will give us, you know, the vector for 1 step in the x direction. And we can just keep adding this to our texture coordinate iteratively to get our new texture coordinate. So that's the scan step, the step in the x scanning direction. Whew, we're getting there. We're doing it. We're doing it live. Fuck it. Now we need to calculate the pre-step. Let me see here. So I want vec2 t, which is going to be our final texture coordinate, which is just t edge, t scan step. This has got to be x0 minus px0. So again, this is the difference between, x0 is going to be our integer. That's the actual pixel that we start on. And this is the x coordinate of the left side of the triangle on the current scan line. So this is the real edge of the triangle. And this is the first pixel that's drawn on the left side of the triangle. We take the difference between that, we multiply that by the scan step, and we add that to the left edge to get our pre-step for the current scan line. So for example, oh geez, so messy. The diagram is getting so messy. This is why I should be using more layers, but I just can't remember. Not when you're in the heat of the moment, as they say. Passionate programming tutorialization. You saw it here first, people. Now, let's say we're doing this scan line here. Our start pixel is going to be this pixel, but the real edge of the triangle is here. So this is the difference. So this is how much we have to step in. So we want to step in, you know, that much into here so that we're starting at the right point in the texture coordinate. Pre-steppin', goose steppin', la-di-da. Sometimes you just gotta say la-di-da. Alright, and now we do our looping in the x direction. So this is gonna draw the actual pixels of the scan line. I'm just gonna paste this all in here. So we want to start from x0, we want to go to x1. Did I do that right here? Y start, a Y end. Why didn't I do X start and X end? I did X0, X1. I don't know, man. Sometimes I don't know about me. You don't know about me. Hell, I don't even know about me. And for every movement, every step we take in the X direction along the scan line, we also want to increment our texture coordinates in texture space. So here's where we actually put the pixel. We go text, we get pixel from our texture, which is just going to be the X coordinate of our texture thing. And here we actually do want to just round to the nearest. So we're going to add 0.5. I know that there's probably functions to round to the nearest that'll make it a little more, I don't know, self-documenting, but fuck it. I'm just going to add 0.5 and then convert to unsigned int. And that's, we'll round to the closest texel, or the closest pixel in the texture to where our texture coordinates are at. And we'll get that pixel and we'll fire it onto the back buffer with put pixel, and that's it. There we have our flat top triangle text all set up, all done up for your viewing pleasure. Now, to draw a flat bottom triangle, it's very similar, but there are some differences. We're going to copy and paste, and we're going to try to modify this one using our knowledge of stuff. And we're going to wonder why it did that. But we're not going to wonder for too long. Flat bottom triangle. All right. Why are you still all red? May not be redeclared outside its class. Okay. I don't understand. Oh. Okay. How about that? Okay, that's better. Okay, there you go. Fair enough. I retract my objection. Case dismissed. There we go. Okay, so what do we got to do to make this not fuck everything up? All right, so we want to calculate our slopes. Now we're doing a flat bottom triangle. So this is going to be V. Well, let's use my tablet to make my drawing just a little bit more legible. Wait, this, fuck. It's going to be V0, be V1, and be V2. So it's going to be V0 minus V0 to V1 and V0 to V2. So M1, V0 to V1, 0 to 1, and this one's going to be 0 to 2, 0 to 2. All right, now the Y start is going to start at V0, and it's going to end at V2. That's the same. That doesn't change. Here we want a UV edge step. All right, so we want to go from V0 to V1. And V0 to V2. Wait, what? Wait, what? Ah, right. So this is basically the, doesn't matter, no, does it? Now I'm doubting myself. So this is a flat bottom triangle. Is this right? V2 minus, so that's the distance. That's the distance traveled from V0 to V2, which is the whole y length of the triangle, the height of the triangle, if you will. This is the height of the triangle. This, where's my other one? Fuck. Wait, what about this one? Where am I? Who stole my pants? Okay, that's the whole height of the triangle. This is going to be the height of the triangle. That's fine. It could be 2, it could be 1, it doesn't matter. The important thing is that we want to go from V0 to V1, and we want to go from V0 to V2. So that's right. Down on down in the water, out in the street? I forget. Down on the corner, out in the street. What am I talking about? My brain is fried. Okay. Y start minus V. Calculate UV edge pre-step. This should be V0. In fact, I'm going to make it V0 up here, although it doesn't matter. Right? Because in a flat top triangle, V0 and V1 have the same Y. I'm going to make it 0 anyways, because I feel like that is more indicative of a start. Okay, so we want V0, Y start, Y end. We subtract that, multiply that. That's all fine. We still want to go to the start and the end. Calculate start and end points. Okay, here we're going to need some changes. This is going to be the slope from V0. Oh no, because that's reflected in here. The change is reflected in here, so this actually should stay the same. Maybe. Oh. Mommy, no. It's got to both be V0. Because it has to be the start point, and the start point is only V0. Dot Y. Oh no. Did I do something wrong here? Alright, because with a flat top triangle, you have two different start points. V0 and V1. You're starting from here, you're starting from here. With a flat bottom triangle, you have one start point. And the only thing that changes for the left and right are the slopes. So this is good. Alright, we're almost there. This shouldn't have to change. Maybe it should? No, this should be the same. This should be the same. Same. Yep, that's the same. This is the same. This is the same. We're done. Woo, we're done. All right. We're done, and it's not even an hour and a half. I'm happy with that. I am happy with that result. Let's try to build this solution. Just make sure I didn't have any horrible syntax errors. Transblit is not a member of... Okay, yeah. We're not playing that game anymore, my friend. We're playing a whole new game. It's a whole new ball game, people. And we are gonna try to implement this mother. So, let's do it. We want to do graphics dot draw triangle text. We need vertices. How did I do it in my other one? That's a good question. Glad I asked it. Because I did not do the transform in the draw triangle function. I know that. Draw triangle text. You know, there's no transformation happening here, so I must have done it in game. I did it like this. Oh, I used an array. That was way smarter than what I did here. I'm gonna use an array. That's what I'm gonna do. And interesting. I didn't go minus 80 to plus 80. I went minus 80 to plus 79, which might also be the right thing to do, but it also might be the not right thing to do. Yes. Anyways, if it's the not right thing to do, the difference will be very small. You won't even notice. You're going to like the way you look. I promise. So, we want to include array. Because I think that's it. No, it didn't. It kind of didn't like it, but then it did. Now, P's are now going to be V's. So we want to change our P's into V's. And I want to change our Q's into T's. Okay, so here we have our quad, which is just 4 vertices, arrayed much like you saw me do before, which is kind of a waste of time, but whatever. Whatever. That's just our matrox, and here we do our transformation. So we have a separate thing for our thing, and then we do the hokey pokey. There we go. How's that? Trans is not it. Oh yeah, because it's tranny, not tram me. How's that? How you like that? Yeah, it's wrong. I knew it was wrong. Okay. Okay, good. Now we're cooking with gasoline, which, as I mentioned before, is not a good idea. Okay, now we can do the thing that we have to do. Trans 0 quad trans. I said z. Didn't you hear me? Do as I say, not as I type. Quad trans 3. And then we want a clip. But I don't have a clipping thing, do I? Shit. Shit. Okay, we'll just copy this. This is just a rectangle that corresponds to the screen dimensions. Dimension. That's how you say it in French. In Francais. And then texture. I don't know. What did I call it? How am I supposed to be expected to remember all these things? All these things. Image. Image. See, now you're getting language lessons on top of it. Shit, man. I'm the white Jesus. Okay. 0. No, the next one is going to be 1. I guess I should keep going clockwise. So 1, 2, 3. 1, 2, 3. 0, 1, 3. 1, 2, 3. And again, this stuff is the same. All right. I think we did it. I think we've saved Christmas. It's a Christmas miracle. Build. I have no faith that this is going to work properly in the first run through. Oh, Jesus. Jeezum crow. Okay, well. I didn't really expect it to crash, though. So, if you could not do that ever again. No? Okay. Build errors. Oh, okay. Well, wait a minute. Oh, we could use width and height, which is actually the things that we should be using, because this is only an image. It doesn't have to be the size of the screen. So I should have been using width and height the whole time. So I guess thank you for telling me eventually, Mr. Compiler. Okay, assertion failed. X is less than width. Right. Okay. Retry. Break. Where's my call stack? Draw flat bottom triangle. X and Y. Where's my X? Where's my Y? X is 400. Y is... Why is that a problem again? Wait, is it get? It's get pixel. So I'm trying to read outside of the... This is the one that I did that I copied and pasted. So it's probably a problem with my copy and pasting. All right, we go from x0 to x1. It's probably in the calculation of x0 and x1, maybe. x0 and x1 seems alright. Wait a minute. Clip.left, clip.right. No, that's fine. This doesn't seem like it would be any different. What about this one? M px0 px1. m0 m1 times y0. Yeah, that seems right. That seems right. That seems alright. What about this one? Okay, v0 to v1. v0 to v2. Yeah, that seems alright. This one's v0 v1, v0 to v2. Jesus Christ. T is negative 76. Seems wrong. Okay. Right. So the problem isn't x and y, it's t.x, t.y. So I'm looking at the wrong things here, aren't I? I should be looking at right. That seems wrong. Texture coordinates should never be negative for this bullshit. Alright. Scan step left. That's fine. All this stuff in here shouldn't really change much. It's got to be up here. T edge. V0 to V1. V0 to V2. For the right side. V0 to V1. V0 to V1. Right, because it's a flat bottom triangle, so that should be alright. V1.t, V2.t. Right. So we're starting at V0. So we want to start at V0 and then add our pre-step into that to find our starting edge values. Okay, and as an added bonus, we should be here. We're starting at V0 and V1, not V1 and V2. So let's fix that bullshit. That's what you get for copy and pasting. You always fuck something up. You always forget to change some value somewhere. But you still do it every single time. Let's try to start without debugging. Oh, we did it. We did it. Look at this. Look at the ship. Look at the dong ship. It's spinning. Helicopter dick. I remembered it this time. So yeah, that's what it is. And you don't have all those dumb holes in the ship. You wanna see? Let's zoom in that motherfucker. Look at that. Isn't that beautiful? That is not a flaccid ship. It is turgid. It is tumescent. I love it. Oh, look at all those. Look at those pixels. Look at all them pixels. That's quite a pixel. And we can zoom her out too to really small. And there you go. That's texture mapping for you. Alright. Oh, my desk is falling apart. That was the sound of a bolt falling out of my desk. So. And we seem to get an error when I close. We'll just ignore that for now. Alright. The police are coming. We gotta make this quick. What do I want to do? Okay, so quickly, we still have a little bit We're not quite there yet. We're almost there, but we're not quite there. We've got to go to d3dgraphics.h. Maybe D3D graphics. I forget which one. Okay, we take the fill value. We're going to make the background white. We're going to take a look. I'm going to go release. And we're going to take a look at what that does for us. Yeah, it does this. Because although we're drawing our ship, we're not taking into account the transparent pixels. So that's not going to be good for a game situation. Wow. Yeah. Not good. Okay. So what do we do about that? Oh, it's very simple. Now my image loading program takes into account alpha. So we already have an alpha channel that works in our surface, texture surface thing. All we got to do is we'll do the hokey pokey. We turn ourselves around. That's what it's all about. Where's the thing? Here it is. So draw flat. Here it is. Here we go. So instead of doing put pixel and get pixel like this, we could do it two ways. We could use alpha put pixel and put pixel alpha on there, alpha blend, which would be nice. But for our ship, we don't actually have translucent pixels. They're all either completely opaque or completely transparent. So what we're going to do is just going to do simple test. If, so we're going to do constant color texel is equal to get pixel, text.getPixel, like that. If texel dot x, which is our alpha value, is equal to, now I think alpha 255 means completely transparent, but I'm not sure. Could be backwards. Wait. If texel is equal to 0, no, 255, I forget which one it is. We'll see. We shall see. Then draw the texel. And there we go. We got to do this on the other one too. They're the same, so we can just copy and paste. If I'm mistaken, well, then I guess we'll have a rude awakening. Start without debugging. There we go. So I was right. And that is how you do. This is how we do. Beautiful. Look at that. Amazing. Okay. Let's go back to graphics, toggle. Let's make this black again. Black, whole sun, won't you come? Start. No, I don't want to debug. I regret everything. There we go. Lovely. Lovely, lovely, lovely. What else? Nothing else really. We're done. Two things I want you to notice here. Take note of. As you zoom this motherfucker in and it gets super pixelated. You can see like the single pixels. Very well defined pixels there. That style is actually really popular these days. I don't know if you've noticed, but the real pixelated style. And then like using rotations and stuff on those pixels. It's all the craze with the kids today's. And that's good. But often what you want to do is when you're zooming something in, you want to make it a little smoother. So instead of just doing nearest neighbor sampling, which is where nearest neighbor sampling is exactly this, where you just round to the nearest texture coordinate. What you could do, let's see if I can find my stuff. What you could do is you could do texture filtering. You could do bilinear filtering, which basically takes the nearest 4. So let's say you've got a texture here, and you've got texture coordinates, and you want to sample So with nearest neighbor, you just pick this one because it's closest. But with bilinear filtering, what you do is you interpolate between these two, and you interpolate between these two to get these 2 points, and then you interpolate between here and here to get your final. So you interpolate between four pixels in the texture to get your final texel. And that gives you something like this. So this is nearest neighbor, and this is bilinear. It's smoother. And then there's trilinear, which is a little sharper than bilinear. It's also more expensive. But yeah. So bilinear filtering is usually what they use when you're drawing textures in a 3D engine. You don't usually use nearest neighbor. It looks like ass. But nearest neighbor is often used in things like indie games, 2D side-scrolling indie game type deals where you want those big chunky pixely graphics. What else did I want to talk about? Oh yeah. So obviously you don't want to resize your image too big because it's going to start to look like ass. Jesus Christ. Jesus Christ! There we go. Sometimes I forget what I'm about to do. Actually, I usually forget what I'm about to do. So yeah, too big looks kind of dumb. Also, too small is not a good thing either. It looks weird. I mean, I don't know if you can tell, but I don't know. It's hard to explain why it's weird, but basically it's because you're skipping a bunch of texels. When you make it small, you're skipping lots of texels. And what it really looks bad is it looks bad when you have a lot of noise in your image, especially, or a high frequency image. And how you can solve that problem is when you're resizing from a very large size, let's say from 100 by 100 to, let's say, 10 by 10, instead of just taking every 10th pixel, as you would normally do with texture mapping, what you would do first of all is you would average blocks of 10 by 10 pixels. You would add them all together and then divide by 100 to get your resulting pixel in your resized image, right? So if you had a really big image like this, you would add this block together, divide by 100 to get this pixel in the image. You do that for each one here. And by averaging all the pixels before you do your transformation, you get a much better looking image. And what you can do is basically you want to be within a power of 2 of your destination size. So let's say you wanted to resize to, I don't know, 9 by 9. What you would do is then you would resize down, first you would resize down to 10 by 10, and then you would use texture mapping to go to 9 by 9, preferably with bilinear filtering. So yeah, averaging pixels together. But the problem is that's a lot to do at runtime. So what you get is you get a MIP map. And what happens is when you load a texture into memory, it will load the texture at the full size, but it'll also generate a texture at a half size and quarter size and so on and so on. And then when you're texturing something, when you're drawing the texture, it will select the one that's closest to your desired size, and then it will perform bilinear filtering. And that gives you much better stuff. So yeah, that's what a MIP map is. And textures are often stored like this in memory. So they take more memory up than the actual texture size, because you've got to store all the reduced size MIP maps. But it's not a lot more space, and it saves a lot on runtime calculations. So you can read up on MIP maps here on Wikipedia if you're interested. But we're not gonna implement bilinear filtering or MIP maps in the current tutorial series. Just wanted to give you guys a basic idea of how this mapping works. Because the idea of mapping from one value to another not only applies to graphics, but to a whole bunch of different things. It is a useful concept, but it's also useful to understand this stuff when you go on to do programming the hardware, because it's quite similar. Yeah, that's about it. I think we're just about done. All right, so I said we were done, but I was mistaken. We haven't actually put the ship into the game, which was, you know, ostensibly the whole purpose of this exercise. So allow us to rectify that right now. Let's restore the game back to its former glory, as we are wont to do. Build that. Start without debugging. Okay. Alright, so game is functioning. Now we want to turn this, we want to replace this wireframe model of the ship with our textured quad. So what we're going to do is we're going to modify ship.h to get that texture information in there. So let's include array. And let's include vertex. We don't need the model anymore because we're going to go for std array. We want an array of vertices, 4 of them. We're going to call this, I'm just going to call this the quad. And we also want surface ship texture. That should be all we need. Now what I would normally want to do is, let's see here. Let's go back to game. What I would do is I would make array a constant and then initialize it in the initializer list. That's how I would normally want to do things, because you don't want the model of the ship to change at any point. You want it to remain static. But from the point of view of being able to copy and paste, it's much nicer if I just leave it as a non-static thing. And I can just copy this bullshit, paste it in here, uncomment it, and we are off to the races. So I will refrain from indulging my OCD this time. Can't make any promises about next time though. Alright, so we don't need this image anymore, so let's get rid of that. And let's toggle and get rid of it from here as well. Let's go back to ship. Alright, so what do we want to do? We want to modify our rasterize function. We're not going to be doing this bullshit anymore. What we're going to do instead is we're going to create a new array for the purposes of holding the transformed vertices. Control EU. Alright. Quad trans equal to quad. Non-static member must be relevant to a specific object. I don't really get that. What is it called here? It's called quad, right? Quad. Okay, and here we assign that. That's all fine. Okay, I got it. I understand. It's because this is a different class. This is the drawable class, and it has a reference to parent. So we got to do that. And we got to do that. Now the transformation is going to be trans. So we'll do that. And then we'll call GFX dot draw triangle text. And we're going to copy and paste for this too, because because we can. And we'll copy that, and let's go back and uncomment. Okay, that's good, that's good, that's good. This is gonna be clip, which I believe is the name of our clipping rectangle associated with this drawable object. And ship texture. I thought that was the name of the thing. Oh, right. I did it again, didn't I? Parent dot ship texture. Okay. And there we go. That should be all we need. Well, there'll be a little tweak, but we'll get there in a second. Let's build this. Alright, let's see if this totally fucks up. It doesn't. Well, I mean, it sort of does. But here we go. Here's our ship. Obviously, we have a slight problem in our scale here, but that can be rectified easily enough. The general idea is sound here. So let's go down here. We could either make the shield radius larger, or we could make the ship smaller. Let's just make the radius larger because I'm lazy. Let's make it 160. Build. Start with debugging. There we go. Now, yeah, there we go. All right, now our ship is not going to be able to fit anywhere. Yeah, we're stuck. We are stuck. But it's working. It is working like a motherfucker. And yeah, I didn't implement zooming in and out, so that won't be a thing. But yeah, that's how you do it. And back to me of the past. And next lesson, not next lesson, but next video, I am going to propose to you guys a little bit of a democratic experiment here. And we're going to see how we proceed with the tutorials, whether we continue on with the current engine and make it into an actual game, and maybe, you know, teach a few more advanced topics along the way, like, I don't know, threading, multi-threading, or maybe SSE optimization. And that's one option. Or the other option will be to, you know, ejaculate from the current tutorial series and start a new series on 3D graphics, because we now have all the basic concepts that we need to go to 3D. We have the idea of vectors and matrices and things like texture mapping, all that good stuff. So now we can take a look at 3D graphics if you want, but that's for the next video. I'll set that up. I'll give you guys a whole presentation, and then you guys can vote on the forums. But for today, we're done. We're done texturing. Took less than 2 hours, which is, I think, pretty good. And if you like the video, click the like button. That would make me pretty happy. I'm not gonna lie. If you didn't like the video, well, I'm sorry. It's the best I can do. I'm hungry and I need to, you know, eat now. I can't record. I can't like stop and re-record this all this bullshit. Not happening. But I hope you liked it, and I hope you'll give me a thumbs up, and I hope to see you next time I upload a video. But until then, this is the Captain Chili of the USS Turgidity signing out.